So I'll go ahead and get started. So welcome everyone again to the Friday Happy Math Hour. I will be covering the Math 1324 for today's presentation. And today's presentation, we're going over systems of linear equations. Okay. So what are systems of linear equations? Well, we have seen in this class already linear equations, but now what we're going to be looking at is more than one line at the same time. Okay, and what we want to do is basically we're going to solve for these graphs or these lines, and the solutions for these are where we have a same an x and y value for all the lines that we draw on the same rectangular coordinate system. Now, there's several ways of doing this. One way is to graph the lines. Another way, which will be algebraically, is by substitution and elimination method. Both of these are done algebraically, and hopefully we also get to see some application problems that involve the two variables. We'll also see larger systems of linear equations where um, technically it's like a 3D version of the lines, yes? And we'll hopefully touch on matrix methods and applications. So again, just to get ready to solve systems of linear equations, let's look at exactly what we need to do. As I mentioned to you, when we're solving for linear systems, especially if we're giving two lines, what we want to find out is where these two lines have a common x value and common y value. And again, if I were to graph these, that value corresponds to the intersection. Okay. So if we have this problem number one here, we want to test this point, negative 1, 3. Is this point a solution for these two lines? And for it to be a solution, it has to satisfy uh, both lines, meaning I have to have a true statement for both. So again, let's go ahead and get started. So what I'm going to do is I'm going to plug in negative 1 for x and 3 for y for each one of these equations. So let's start with the first one. I'm going to call the first one equation 1, and I'm going to call the second one equation 2. Okay, so again, I'm going to start with equation 1, the first one, and everywhere I see x, again, I'm going to plug in negative 1, and for y, I'm going to plug in 3. So here we have x is negative 1, y is 3. Okay, so 2 times negative 1 is a negative 2, and negative 2 plus 3 is 1. Okay, so when I subtract negative 2 plus 3, I get 1 equals 1. So this is giving me a true statement. So this point, negative 1, 3, is a point on the graph, or it is a point on this line. But again, for it to be a solution for a system, it also has to match the other line. So I'm going to take the equation 2, and I'm going to do the same process. I'm going to replace the x with a negative 1 and the y with a positive 3. So a negative 3 times a negative 1 is a positive 3. 2 times 3 is 6. And 3 plus 6 is 9. I have a true statement. Okay. So for this particular one, negative 1, 3 makes both equations true. Then the ordered pair is a solution of the system. Okay, so let's look at this next example. Let me test this point, 2, negative 5, with these two equations. Again, I want to label them. So I'll take equations 1 and 2, and I'll start with equation 1. And everywhere I see x on this particular one, I'm going to replace it with 2. Everywhere I see y, I'm going to replace it with a negative 0.5. Okay, so 0.5 times 2 is 1, and 8 times a negative 0.5 is a negative 4. So 1 minus 4 is a negative 3. Yes? So this is the true statement. Okay, now I'm going to plug the same ordered pair into my equation 2. Again, everywhere I see x, I'm plugging in 2, where for y, I'm plugging in a negative 0.5. So 5 times a negative 0.5 is a negative 2.5. 2 minus a 2.5 is a minus 0.5, but minus 0.5 is not equal to minus 5. So in this particular example, since this is not a true statement, then this point is not a solution for this system or these two equations. And that's what we're going to call systems. Systems are when we're evaluating more than one line at a time. Okay. Um, and for the point to be a solution, again, it has to give us a true statement for both lines, or for as many lines as we're looking at. So again, number one was a solution. Number two is not a solution. Okay. So these are the types of answers that we may get doing our homeworks for this section. Okay. Again, if I was applying the graphing method, for the first method, we have two lines. Okay. The point of intersection um, um, is the solution. Okay. When we have exactly one answer, okay, this we'll have a one solution is will have a unique value. We'll have a value for x and we'll have a value for y. Okay. So an example for this problem, again, my x equals 3, y equals -2 is my solution for that first graph here. Okay. Now, if you look at the second graph here, um, even though they might look different here, if I were to convert these into slope-intercept form, okay, I would discover that these two may look different, but it's the exactly same line. They would have the same slope and same y-intercept. So there's two ways you can look at it. You can look at these two lines as just being one line, okay, or you can think of it as one line on top of another line. So when we have this case where we have the same slope and same y-intercept, meaning it's producing the same line, the answer for this is infinite number of solutions. Okay, so that's what we'll have. Okay, and again, some other examples you'll see when you're solving for this, if you get these true statements like a number equals to another number, or you have 0 equals to 0, what that means is that you're dealing with the same line, hence you're dealing with infinite number of solutions. Okay. Now, there is now just one x and y value. Okay, but if I look at this next one, okay, again, if I graph these two, um, and if I were to convert these into slope-intercept form, I would discover that these two equations have the same slope but different y-intercepts, and what that creates is parallel lines. Since these two lines are parallel, they will never intersect, they will never cross, hence they'll never share any values. So in this particular problem, when we have two lines that never intersect, in other words, they are parallel, we have no solution. Okay. Now, if you were solving for these algebraically, the way you're going to discover that these are they don't intersect is you'll have false statements when you're trying to solve for the equations. Okay. So you'll get either 3 equals 2 or number equals to another number. Okay. All right. So, and there's again no x and y value for these. Okay. Again, hopefully this is a lot of review from 2.1. Okay. So the first one, when we have one solution, the book calls this a consistent independent system. Okay. When we have infinite number of solutions, we call this a consistent dependent system. And we have no solution, we call this an inconsistent system. Okay. All right. Now, so let's practice one of the methods to solve a system. And the first method is by graphing. So in this particular case, we have y is equal to 3x minus 6, and we have minus 5x minus 2y equals to -10. Okay, so equation 1 is already set for me to ideally graph. It's giving it to me in slope-intercept form. So I can get my 2 points to graph. My first point, or my second point, I'm going to get it from my slope, which is 3 over 1. And I'm going to use the y-intercept, the b value of this, which is -6. So here, when I go to my graph, the first thing that I would graph is my y-intercept. And it's here at -0.6. And since my slope is 3 over 1, I'm going to rise 3 and run 1. Okay, so I go up 3 and run 1. There's my other point. Connect the two dots, and there's my line. Okay, so that's the first line. Now let's go ahead and use the second equation. Now for me, what I would like to do is, This one's in general form. Let me go ahead and convert it into its slope-intercept form. This allows me to graph really easy. So that's just solving for y. Okay, so the first thing that I'll do is I'll add 5x on both sides. Then I'm going to divide by a -2 on both sides. And it's going to give me this equation. Y is equal to -5 x plus 5. So on this particular problem, I have a y-intercept at 5. Okay, and my slope is -5/2. So I first plot my y-intercept. Here it is, 5. And since my slope is negative, I'm going to go down 5 and then run 2. Okay, so and here I am. So when I connect these two dots, now we can see what is the x and y value that these two lines share. Well, it's at this point, at 2, 0. Yes? So this is the intersection. This means that this is my solution. Okay, so as you might imagine, okay, this one is very easy to see the solution, but what if that intersection was between numbers? It would be very hard for us to determine the exact value using a graphing method, right? So again, just to review, this is called a consistent independent system. Okay, but um, to get an accurate method of solving, especially if we have a point that lies between 2 points, we are going to use this method called the substitution method. And just like the name sounds, like for instance, if your teacher had told you, next week you're going to have a substitute, that means someone else is going to replace your teacher to do your class. So this is the same concept for solving linear systems. The substitution method says this: you can use any of the two equations and solve for one of the variables, and then you're going to replace that variable into the other equation, and then you just algebraically solve. So in this particular problem, they did half of the work for us already. They solved for y on their first equation, if you see. So that's what I'm going to use. I'm not going to do any more work. I'm going to take that to my advantage. Since I have already a variable solved for, which is y, I'm going to replace that y value into the second equation. Okay. So here, my first equation again was solved for y already, and I'm going to replace that y value into the second equation. So this is my second equation, minus 5x minus 2y equals -10. And everywhere I see y, I'm going to replace it with this value, 3x minus 6. Okay, so here we have y, and I'm going to put in the 3x minus 6. So the first thing I'm going to do is I'm going to distribute that -2, and I'm going to get -6x plus 12. Okay, I'm going to combine my like terms. Minus 5x minus 6x is going to give me minus 11x plus 12. I'm going to move the 12 to the other side by subtracting 12 on both sides. And this is going to give me negative 11x is equal to negative 22. And then the last step is dividing by a negative 11 on both sides. And when I do that, I have x equals 2. So this is the x value that is shared by both of these lines. Okay, so to get my y value, since my first equation is already set up to give me the y value, I'm going to replace this x value into the first equation. Okay, and again, it doesn't matter which one you place it into. I'm just being nice to myself, and since the first one is already set up for me to give me the answer, I'm going to use the first equation. Okay, always make your life easy. Okay, math is easy if we make it easy. All right, so again, I'm going to use the first equation to get my y value. So again, everywhere I see x, I'm going to replace it by 2. So I plug in my 2. So 3 times 2 is 6. 6 minus 6 is 0. So my y value is 0. So the solution using the substitution method for this system is going to be x equals 2, y equals 0. Again, my ordered pair is 2, 0. Okay, so this is the substitution method. We have another way to solve systems, and this is called the elimination method. I think your book also calls it, sometimes it mentions it as the addition method. Some other books call it the addition by elimination method. So, but they all mean the same thing. And just like the name sounds, okay, elimination means you want to get rid of one of the variables, and once you do that, you'll end up with one equation with one unknown. Okay, so you want to add these two equations in a way where you can cancel one of the variables. So for me, for the first thing that I need to do with these two equations, um, I need to place the first one into its general form. That way I can add them and cancel something out. So again, equation one is in general form. Let me put it in, excuse me, is in slope-intercept form. Let me put it into its proper general form. Okay, so to do that, it just means I'm going to move the 3x to the left. Okay, so I'm going to subtract 3x on both sides, and just by doing this, I made it back into its general form. Okay, so if you see here, when I put it with my other equation, now I can see what variable would I want to eliminate. Again, you want to make things easy for yourself. So for me, the variable to eliminate, I would think, is the y value. Okay, so for me, I want to eliminate the y value because it's going to be easy, because in order to eliminate the y value, that first equation would need to be a 2 there. So I am going to multiply a 2 to an equation. Now, rule of thumb and something to be very, very careful with. Because I want a 2 in that y to eliminate with the other one, and I'm going to multiply 2, I got to make sure that I multiply a 2 to the whole equation, because if I only multiply to a half of it or only to one variable, I either am changing the equation or I'm unbalancing the equation. So you got to make sure that you multiply that value throughout the equation. So I'm going to multiply it 2, and again I'm going to multiply it to both sides. So 2 times a negative 3 is a negative 6. 2 times y is 2y. And 2 times a negative 6 is a negative 12. Okay. Now I am going to add it to that second equation. And look what happens. When I add these two equations together, I have minus 6x plus minus 5x is negative 11x. And 2y minus 2y got eliminated or canceled is 0. Minus 12 plus minus 10 is a negative 22. Now to solve for x, again, I'm going to divide both sides by negative 11. And I'm going to get x equals 2, which is the solution that I had gone before. Okay. Now to solve for the other y value, again, you plug it into any of the two equations. Okay. So again, I'm plugging it into the first one, and you see that I'm going to get 0 again. Okay. So this is called the elimination method or addition method. Okay. All right, so my solution for this problem is 2, 0. Okay, so um, let's try this problem here. Okay, so in this problem, we're going to solve for the elimination method again. Um, why does it look very similar to my other one? Did I? Oh, okay. So it is different. Okay, so on this particular problem, I'm going to first convert the first one to general form. All I had to do was move the 3x, subtract 3x on both sides, and minus 3x plus y equals negative 6. Oh, so what we want to show you with this is that uh, let me eliminate the dx, and just so you can see that I'm going to get the same exact answer. Okay, so instead of eliminating the y's, I'm going to eliminate the x. So the first thing that I have to say to myself is if I want to eliminate the x, I want to get the least common multiple between negative 3 and negative 5. And not only that, when I get the least common multiple, they have to be opposite signs, because that way, when it's the same number with opposite signs, they'll become 0 or cancel each other out. So I see that between 3 and 5, the least common multiple is 15. So what I'm going to do is to eliminate the x's, I need to multiply that negative 3 with a negative 5 to make it an opposite sign and to get my least common multiple, which is 15. So when I multiply negative 5 to a negative 3, it gives me positive 15x. When I multiply negative 5 to y, it gives me negative 5y. And when I multiply negative 5 to a negative 6, that gives me a positive 30. Now again, I want a negative 15x for the second equation. So on that equation, all I'm going to multiply is a positive 3 to this one. So look what happens when I multiply my positive 3 to the second equation. 3 to the negative 5x is going to give me a negative 15x. 3 times a negative 2y is a negative 6y, and 3 times a negative 10 is a negative 30. So when I add these two equations together, okay, I get negative the x cancels. 15x minus 15x is 0. Then I have minus 5y minus 6y is minus 11y is equal to 0. To solve for y, I'm going to divide by a negative 11 on both sides. And when I do that, I had y equals 0. Now to get the x value, I'm going to replace it into either the two equations. It doesn't matter. I'm just going to use the first equation because or let's practice the second one. Okay. Let me use this equation to show you that I'm going to get the same answer. So everywhere I see y, I'm going to plug in 0. Okay. So negative 2 times 0 is 0. 0 minus 5x is minus 5x. So to solve for x, I'm going to divide by a negative 5 on both sides. And when I do that, I have x equals 2. So if you see, I have the same solution as before, which is just 2, 0. Okay, again, and it's a consistent independent system. Mr. Sassi wants you to make sure you get the names right, yes? Okay. Any questions? Again, and I forgot to mention, and just like Mr. Sassi likes to use these PowerPoints, so I can't see anything, okay? So if you have a question, feel free to unmute your mic. You don't have to raise your hand or anything like that, or don't chat me because I don't have access to my chat, okay? So if you any questions arise, please feel free to unmute yourself. There is no problem interrupting me, okay? All right, let's do another example. Let's use the elimination method for this one. Okay, so I have two equations. I like to label them 1 and 2 all the time. Okay, the first one is 3x minus 2y equals to 4, 6x minus 4y equals 8. Again, in this particular one, both of them look easy to eliminate. It doesn't matter who we eliminate. Both of them require us a little bit of work. So what I'm going to do is I'm going to go ahead and get rid of my y's. Okay, and to get rid of my y, I if I wanted to get rid of my y, the minus 4y is I can make it into a 2, but that's multiplying by fractions. I don't want to go that way, but I can make the 2 into a 4. And since I want the opposite sign, I'm going to multiply that negative 2 with a negative 2. That's going to give me a positive 4. That will eliminate with that second equation. But again, I need to multiply that number to the whole equation. So when I do that, negative 2 times 3 is a negative 6x. Negative 2 times a negative 2y is a positive 4y, and the negative 2 times 4 is a negative 8. I don't have to do anything to the second equation because it's going to eliminate automatically my y. So again, I'm going to add these two equations together. So, I have this solution. Everything canceled out. So again, what did I mention happens when this situation happens? That everything canceled out. What this means is that I'm dealing with basically the same line, or I have two lines on top of each other. So then the solution for this problem is an infinite solution. Again, whenever this happens algebraically, that you have 0 equals to 0, or you have a number equals to another number, what that means is that, again, it's the same line, or you have two lines on top of each other, means you have an infinite solution, okay? Or it's called a consistent dependent system, okay? All right, so let's look at this example now. Solve the system by elimination. Okay, again, I like to label them 1 and 2. Okay, um, on this particular problem, I think it would be easy to get rid of the y's again. So yes, so I'm gonna get rid of the y's. So that 5, if I want to get eliminated with a 15, I need to multiply it by a negative 3. The same value, opposite sign. So I'm gonna multiply that negative 3 to my whole equation. Negative 3 times 2 is a negative 6x. Negative 3 times positive 5 is a negative 15y. And the negative 3 times 8 is a negative 24. I'm going to add it directly to equation 2. Don't have to do anything to it. I'm going to add them together. And I have minus 6x plus 6x is 0. Minus 15y plus 15y is 0. But I have negative 24 plus 18 is a negative 6. This is a false statement. When I get this a situation like this where I have a false statement where 0 is not equal to negative 6, what this is telling me is that these two lines are parallel to each other. That means that these two lines will never intersect, hence we don't have a solution. The answer is no solution, or it's called an inconsistent system. Okay? All right, let's go ahead and see where we can apply this for a real world application problem. Okay, so we have this problem, and let's go ahead and read it out. It says a 200-seat theater charges $8 for adults, $5 for children. If all seats were filled and the total ticket income was $1,435, how many adults and how many children were in the audience? Huh. This is not as difficult as you may think, okay? Very easy to solve, okay? So the first thing that we need to do is we need to come up with two equations from this information that we have here. And the first equation, what we can do is something that we have already studied, how to get revenue, right? Revenue is price times quantity. So for instance, we know that we have seats and each seat is worth a different price either for adult or for a child. Okay. So here we're gonna say that the adult seats are X and the Y seats are labeled for the children. Now we know that there are a total of 200 seats, so that means that X plus Y should equal to the 200 seats. Okay, so that would be my first equation. Now, again, the other equation is what I had mentioned to you, where we can use the concept of revenue. Okay, we know that since I made X be the adult tickets, that I know that the adult tickets cost $8. So um, the to get the revenue is price times quantity, 8x. But I'm gonna get a total quantity because this is just part of the problem. I also have children's seats. They are $5 each, and we indicated that the children's seats are the variable y. So to calculate the revenue for children would be 5 times y. So to get the total revenue, if I add these two quantities, they should equal to my total income, which they gave me, which was $1,435. So my total income is this $1,435. So to get this equation, I add these two variables together. 8x plus 5y should equal the total income, 1,434. Now, if you notice, now we have two equations. Hence, we have a linear system. Okay, and I can use any method that I want in order to solve for this. So let's see, how are we going to solve for this? So these are my two equations, equations one, equation two, and by the looks of it, we're going to use the elimination method. Okay, so I'm going to eliminate the x value. Okay, so to eliminate the x value, if you see, my second equation is 8x. So I want to make that 1 into a negative 8. Okay, so I'm going to multiply negative 8 to the whole equation. So negative 8 times x is negative 8x. Negative 8 times y is a negative 8y. And the negative 8 times 200 is a negative 1600. Okay, the second equation, I'm not going to do anything to it because it's already set up for me to eliminate my x. Let's just add them together. Negative 8x plus 8x is 0. Negative 8y plus 5y is a negative 3y. And the negative 1600 minus 1435 is going to give me a negative 165. Divide by a negative 3 on both sides, and I'm going to get y equals to 55. So what this means is that to get my total income of $1,435, I sold 55 children tickets. Okay, so now I'm missing to get the adult tickets. So to do that, I can replace this y into any of the two equations. But again, I'm going to be nice to myself. I'm going to pick that first equation. I think that first equation is the easiest one to use. Okay, so I'm going to use the x plus y equals to 200. Again, I'm going to replace the y with 55. So x plus 55 is equal to 200. So to solve for x, I'm going to subtract 55 on both sides, and I'm going to get x is equal to 145. So what this is saying is that I sold 145 adult tickets. So that is my solution here. 145 adults, 55 children. Again, and I was able to solve this application problem again, solving using linear systems. Okay. All right. So when we are dealing with larger systems of linear equations, what that means is we're probably going to deal with more than one line and more than one variable. So one of the ways I like to tell my students is you saw that we had an x and y value. That's just like a flat surface, right? But when we have z, I like to think of z as this line is like coming towards you, like a 3D effect, okay? So the way to solve these types of systems when we have larger systems is something called um, back substitution. Okay, so here we have these equations, and I'm going to label them 1, 2, and 3. Okay, so um, if possible, what we want to do is we want to rearrange this where we have only one unknown. Okay, or when we have one equation equals to 1. So um, the way that I'm going to do this, since I can't do that, since I don't have one answer to do my backward substitution, what I'm going to do is I'm going to use two equations at one time to get rid of the variables one at a time. Okay, let me tell you what I mean. Okay, so I have these equations again. I have um, um, 1, 2, and 3. But what Mr. Isasi did right here again, he just put them in order. He rearranged them where the first one had a 1 and the for the first coefficient for the x, and then the other ones followed suit 2, 3. Now you don't have to do this, but this does make your life a little bit simpler. Okay. All right. So the first thing that I'm gonna do is so what's the plan, right? So my plan is I'm gonna grab equations 1 and 2, and I'm gonna eliminate one of the variables. Okay, so um, once I do that, I'm gonna take a different order. Then I'm gonna take equations 1 and 3, and I'm gonna eliminate the same variable that I eliminated from equations 1 and 2. And when I do this, the solutions for these two is gonna leave me with two lines that have only two variables, and now it's just the same work that we did before. Okay, so let's start by eliminating the x variable. Okay, so equations 1 and 2 will create a new equation 2, and when I eliminate the x variable from equations 1 and 3, it's going to give me a new equation 3. Okay, now with these two equations, I'm going to eliminate now the y variable, and that's just going to leave me with one unknown, the z value. Once I have the z value, then I will be able to do back substitution and solve for the system of equations. Okay, so let's get to it. Okay, these are the steps that you should look out for. Okay, all right. So when I do this, this is what it's gonna look like. Okay, and it's gonna look like this, and I call this process back substitution, where I have one unknown, and then I place that one unknown to where I have two unknowns, and then I place those two unknowns to where I have three unknowns. Okay, so it's called again back substitution. So let's go ahead and do it. All right. So again, I'm gonna get these equations. I'm gonna start with equations 1 and 2. Okay. I want to eliminate the x value. So I'm going to multiply a -2 to that first equation. That's going to give me -2x plus 6y minus 4z equals 0. I'm going to add it directly to equation 2. Don't have to do anything to that. I'm going to add them together, and it's going to give me 4y minus 3z equals 3. Okay. Now I'm going to take a different order, and I'm going to use my equation 1 again. I'm going to get equations 1 and 3. Okay, so equation 1 is x minus 3y plus 2z equals 0. Equation 3 is 3x plus y minus z equals 7. I want to eliminate the x, so I want to multiply equation 1 with a -3. Okay, so let me do that. I'm going to get this. I'm going to add it to my equation 2, and let me see, I eliminated my y value. This gave me a new equation 3. So these are my two new equations. And if you see, now I'm done just to two variables. Okay, so I'm going to take it another step, and I'm going to use these two new equations to eliminate my y value. Okay, so what I'm going to do is I'm going to multiply the first equation by a -10, and I'm going to multiply the second equation by a +4. Okay, again, we always want to have opposite signs, so that's why I'm multiplying one with a negative. Okay, and since um, my least common multiple between 4 and 10 was the 40, that's what I'm using. Okay, so again, when I multiply -10 to equation 1, I get -40y plus 30z equals to -30. 4 times the second equation is 40y minus 28z is equal to 28. And when I add these two equations together, you see that I have 2z equals to -2. To solve for z, just divide both sides by 2. And I have z equals to -1. Now, I do want to point out that the way Mr. Sazi set this up is just, it makes it straightforward. You know, you're eliminating one variable at a time in order, but you don't have to follow this order, okay? You can eliminate it in any order you want. You can eliminate the y's first. You don't have to rearrange them from the beginning. He's just trying to make the problem nice. Now, sometimes you're able to do that, but sometimes you're not able to do that. So, but again, this setup is to help you see the method clearly. Okay, so now you see that I can work myself backwards. Okay, I have these three equations. I'm going to use the first equation, x minus 3y plus 2z equals to 0. And then I'm going to use one of the two equations. It doesn't matter which one I use. I can use the 2 or the 3. In this case, I'm using the easy one. I'm using the 4y minus 3z equals to 3. And I have z equals to -1. Okay, so the back substitution, it just works this way. Okay, I'm going to replace that second equation with the z value that I already have, which is -1. So when I do this, I have 4y plus 3 equals to 3. Subtract 3 on both sides. I have 4y equals to 0. Divide by 4 on both sides. I have y equals to 0. So now I have two values. I have the z value, which is -1, and I have the y value, that's 0. I'm going to plug that to the first equation. So the first equation is this. So these are the values that I have now. Let me place them. Y is 0, z is -1. So -3 times 0 is 0. Um, 2 times a -1 is a -2. So this leaves me with x minus 2 is equal to 0. Add 2 on both sides, and I have x equals 2. So the solution for this system is 2, 0, -1. We got to make sure that we put them in order. Okay, it's always x, y, and z. Okay, sometimes you'll have 4. It would be x, y, z, and w. Okay, those are the common variables that we use for uh, systems or larger systems of equations. Okay, all right. So let me introduce what's called the Gauss-Jordan elimination. And the Gauss-Jordan elimination is basically the same thing that we were doing algebraically, but we normally do it for linear systems in a matrix form. Okay, so the first thing that we need to do is describe what we call an augmented matrix. We can convert a linear system into a matrix form, and this matrix form again is called an augmented matrix form. Okay, and it's super easy to do this. Okay, um, and once we do this, again, the way we're going to solve is your calculator calls it the RREF, or row reduction elimination form, or again, the math term is called the Gauss-Jordan elimination method. Okay, so let's look at this equation that we had already solved for, that we already know the answers for. And the first thing that I want to show you is how easy I can convert this equation into what's called a matrix equation, or a matrix form, and in this case, an augmented matrix form. And to do that, since matrices hold a placement value for the variables, I don't have to tell it that this is an x value, this is a y value, this is a z value. Okay, the matrix will do that for me. Okay, it keeps a place value. So I'm only going to grab the coefficients of the linear system. So the first thing you need to know is a matrix is represented by brackets. Okay, whenever you see brackets like this means that now we are dealing with a matrix. Okay, and again, I'm gonna only put the coefficients of the values of this of the line. So you see here, x, its coefficient was 1, so that's 1 in that first place, the first row, first column, okay, and so on and so forth, okay. So we have 1, 2, 3, 4 columns because we have 4 columns for our lines, okay. Now the equal sign in augmented matrix is classified as a line. Okay, there's a line here. This line or a pipe is the representation for the equals in augmented matrix. So voila, I've converted a linear system into a matrix form, or in this case, an augmented matrix form. Okay. Now, to solve an augmented matrix, again, we're going to use this concept called RREF, row reduction elimination. Okay, so the row reduction elimination means that you want to have this setup. Okay, you want to have what's called the identity matrix. The identity matrix, that's the values to the left of the equal sign, have to be this. I want to have one solution for the x value and 0 solutions for the um, y and z. So the way you want to think of this identity matrix is like you're solving for the intercepts. To solve for the x, you set everything else equal to 0, and you have the answer for x. For the second row, I want one value for the y, and I'm going to set x equal to 0, z equal to 0, or you're solving for the y-intercept. Okay, and same for the last one. This 1 indicates that I have one solution for the z value, means that's like the intercept. I set x and y equal to 0, and I have my answer for z. Okay, now when you do this, and when you have this in this form, the solution is going to present itself. The solution for the x value is 2, the solution for the y value is 0, and the solution for the z value is -1. Okay, so again, we know this because we solved it before, but let's go ahead and do it. Let me show you how I can get the augmented matrix to look like the identity matrix, which is 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, so let's go ahead and show you how. Okay. So there, it's a three-step plan. Mr. Sazi has a three-step plan. All right. So um, first, he's going to describe how to do it. Okay. So let me just label these matrix as A, B, C, D, E, F, G, H, I, J, K, L. Okay. And what you want to do is this. Yeah, we're letting all these letters be real numbers. Okay. This is just for instruction purposes. Okay. Um, to do the row reduce echelon form or row reduce elimination form, okay, um, we want to have this. We want to have what's called our identity matrix, okay? So to do this process, okay, we're going to label these as row 1, row 2, and row 3, okay? And this is crucial for your homework because your homework is going to ask you to do some of these process and you have to use this syntax, okay? All right, so step 1. What I want to do is I want to get a new row 2 and new row 3 and make those 0. And to do that, I'm going to use row 1 to do that process. Okay, so here I want the row 2 and row 3 under A to be both 0. That's the first step. Okay, then the next step is you're going to get row 2 and you're going to use row 2 to get a new row 1 and a new row 3 and you want B and Q to be 0 now. Okay, so when I do this again, you see that the M stayed the same because I'm using row 3 to get a new row 1 and a new row 2 to make B and Q 0. And then the last step is you're going to use row 3 and to get a new row 1 and a new row 2, okay? And you want the U and N to be 0, okay? So again, here, when you do this last step, you're going to end up with this scenario, and you're going to get the solution for X, Y, and Z, okay? So these are the steps that you want to follow. Now, you must follow these steps because if you don't, you'll go in circles and you'll never solve it. You have to follow these steps, okay? All right, so let's do our three-step plan. Okay, so this is my augmented matrix, and again, I want it to look like this. Okay, so again, um, to do this, okay, I'm just repeating the process since I'm just taking away the letters. I'm using the numbers. Again, this is what's happening within our steps. Okay, great. Let's do this. Okay, this is my augmented matrix. Okay, so the first step is I'm going to use row 1 to get a new row 2 and a new row 3. Okay, so this is row 1, this is row 2, this is row 3. Okay, so let's do this. So row 1 is this. Okay, um, and I want to eliminate that 2, right? So what would I have to multiply to the number 1 to eliminate it with a 2? Well, that would be a negative 2, right? So what I'm going to do is I'm going to multiply a, well, let me finish. And I'm going to eliminate this 3, right? So here, I'm going to multiply negative 2 to row 1, and I'm going to add it to row 2, and that's going to eliminate that 2 there. What do I have to multiply to 1 to eliminate it with a 3? Well, that would be a negative 3. So I'm going to multiply negative 3 to row 1, and I'm going to add it to row 3. If you notice, this is the same thing that we were doing before, but now we're doing it a lot simpler using matrices. Okay, so when I do these, when I add these two together, okay, let's do a little scratch work. Let me show you the multiplication of negative 2 with row 1. When I multiply negative 2, gotta make sure that I multiply to the whole equation. Okay, so I have negative 2, positive 6, negative 4, 0. I'm going to add it directly to row 2. Okay, so negative 2 plus 2 is 0. 6 minus 2 is 4. Minus 4 plus 1 is negative 3. And 0 plus 3 is 3. That is my new row 2. I'm going to put it there. Okay, let's do the same thing. Let's do a little scratch work for the row 3. I'm going to multiply negative 3 to row 1, the whole row 1. Okay, I get this. Negative 3, 9, negative 6, and 0. I'm going to add it just to row 3, just the way it is. And when I do this, as you see, I eliminated that first value, which has represented my x value for the rows 1 and, excuse me, for my rows 2 and 3. Okay, all right, moving on. Gotta go to the next step. The next step is to eliminate that on the second column, that negative 3 and that 10. And to do that, I'm going to use my row 2. Row 2 is this. I'm going to use it to get a new row 1 that is going to eliminate that negative 3. And I'm going to use row 2 to eliminate that 10. So let's do this. So to get rid of that 3, I'm going to multiply a 3 to row 2 and a 4 to row 1. So the least common multiple between negative 3 and 4 is 12. And I don't have to worry about the sign because they're already opposite sides. Yes? Now, what about to get rid of the 10? Well, the least common multiple would be 40. So I need to multiply row 2 with a negative 10 and a 4 to row 3. And on this one, since they had the same sign, I had to multiply one of them to a negative, and I'm just using the first one, the negative 10, to multiply to get rid of it, okay? All right, so let's do my little scratch work. Okay, I'm going to multiply 3 to row 2. I have this. I'm going to multiply a 4 to row 1, and I get this. Now I'm going to add. If you see, I got rid of that second value, okay? I got 4, 0, negative 1, 9, okay? I'm going to do the same thing to get rid of to get a new row 3. Multiply negative 10 to row 2. Multiply a 4 to row 3. And I get this. Add these two together. If you see, I got eliminated my second value. Okay. So we want to simplify. Okay. And the simplification, now you don't have to, but it will make our life simpler. You can leave the simplifying till the end. But in this case, let's go ahead and take care of it. So, and let me show you another syntax. To simplify, what that means is I want to make the numbers smaller. And you only want to do this if if the numbers that you see here still present are all divisible by the same number. And if they're not, I mean, you can simplify, but you might end up with fractions, and you don't want to do that. You'll make your life harder. So on this one, since I have a value of 2 for both, I can simplify, and I can simplify by making it like this. Again, the syntax for this was I multiplied row 3 by the fraction negative 1/2. So if I do this process, again, Mr. Sassi didn't put it, but I'll do it mentally. Negative 1/2 times 0 is 0. Negative 1/2 times 0 is 0. Um, or he's just using the positive 1/2, excuse me. Positive 1/2 times 2 is just 1. And a positive 1/2 times a negative 2 is a negative 1. Okay? All right. So this is where he's getting these values that are simplified. Okay. All right. Now we're to step 3. I want to make that negative 1, that negative 3 above the 1 to be zeros. So I'm going to use my row 3 to get those two new lines. Okay. So my row 3 stays the same. I'm not going to touch it. Okay. But I'm going to use this line to get rid of this negative 1. And I'm going to use this line to get rid of this negative 3. Okay. So again, what do I need to do? So to eliminate row 3 with row 1, I don't have to do anything. They're already the same value, opposite signs. So if I just add these two together, they're going to get eliminated. But on the second one, I need to multiply in 3 to row 3, add it just directly to row 2 because they're opposite signs, and I'm going to eliminate that value. So let's go ahead and do my scratch work. Okay, to row 3, I'm not doing anything. Row 1, I'm not doing anything. I'm just adding them together. Then you see when I add them together, that z value got eliminated. 1 minus 1 is 0, okay? And minus 1 plus 9 is 8. So that's, then we want to simplify again. I'm going to multiply row 1 by a 1/4, okay? That fraction. So 1/4 times 4 is 1. 1/4 times 0 is 0. 1/4 times 0 is 0. And 1/4 times 8 is 2. So technically I divided by 4. Okay, that's what I mean when I'm multiplying by 1/4. Okay, so the new answer for row 1 is this 1002. Okay, let's get the last one. I'm going to multiply it in 3 to row 3, which is going to give me this. I'm gonna add it just directly to row 2. Don't have to do anything to it. And when you see I have this answer, okay, so I'm gonna simplify again. I'm gonna divide by 4. So this is gonna give me 0, 1, 0, 0. So when I do that, do you see that now I have the identity matrix. The left side gave me the 1, 0, 0, 0, 1, 0, 0, 0, 1. The line is the equal sign, and this refers to my solution. My solution is this: x equals 2, y equals 0, z equals negative 1. Okay, so again, these were the steps. I'm going to go kind of quickly because I'm almost out of time. Okay, I'm just going to show you my work. Okay, these were the steps to do this problem. Um, um, I have my first equation. I'm getting a new line 2 and a new line 3. Okay, so there's my line 2. There's my line 3. Okay, now the next step is I'm going to use row 2 to get a new row 1 and a new row 3. Okay, so these are my works. I need to get rid of my y values. So I'll do my steps. Okay, so that's my new row 1. Okay, do the same thing to eliminate and get my new row 3. Okay, and I have this. Okay, again, you have to follow these steps. You first have to eliminate the first column, then the second column, and the third column. Deviate from this and it won't look nice. Okay, all right, the last step is getting my third column. Okay, so again, I'm going to use my row 3 to get a new row 1 and a new row 2. Okay, so this is the process to do that. This is my work to get my new row 1. Okay, and replace it. This is my work to get my new row 2, excuse me. Add them together and I have my solution. My solution for this particular example is x equals 3, y equals 1, z equals negative 1. Okay. All right, how are we doing? All right, I think we're gonna have time, like 3 minutes. Let's just go through this um, application problem. So if you see, it's the same problem as before, except on this one, um, now we added teenager ticket prices, right? We have adults, teenagers, and preteens or kids, right? So there's 570 people in the concert, so that's the number of total tickets sold. Okay, so now let's deal with the people. Let's let X be adults, Y be teenagers, Z be the preteens or the kids. There are 570 total people. So the first equation is x plus y plus z equals 570. Okay, again, let's get our revenue equations to get our total income. So adult tickets are $5, so the revenue is 5 times x. For the teenagers is $3, so the revenue is 3 times y. So for the preteens or kids is 2 times z. Okay, what all this has to add up to my total receipt or my total revenue, which is 1,950. So when I add this all up to be equal to each other, that is my equation. Okay, but if you see here, I need another equation because I have three variables. In order, as the number of variables you have, you need to have the same number of equations. So since I have three variables, I need one more equation. And the word problem gave us this problem, an opportunity to get this third equation. It says 3/4 as many teenagers as preteens attended. So what does this mean? So if my teenagers is Y, if my preteens is Z, it says that 3/4 as many teenagers. So that means if I multiply 3/4 times my kids, that's gonna give me the 3/4 as many teenagers. Okay, so we can flip it. Okay, um, to make it a little bit better, okay? And that is our new equation, okay? We can set it up as y equals 3/4 z, yes? So now we have three equations, three unknowns. We can multiply both sides by 4 on this last equation, okay? Where we have 4y is equal to 3z, okay? Now what I can do with this one is I can substitute that into, um, well, he's wanting to put it in general form. Okay, that's fine. So we have 4y minus 3z equals to 0. Okay, so this is our equation 3. Okay, so I would have solved it from the 4y plus 3z already, but it's okay. Um, but I'll have to stop here. Okay, um, I want you to go ahead and try it again. This presentation will be uploaded later on into our YouTube channel. I want to thank you for joining me today on Friday, and I wish you luck in all your classes. Okay, thank you so much.
Thank you, Mr. Carizales, for your wonderful presentation. Again, we do want to remind everybody about the previously recorded sessions, which are available on the YouTube playlist, and this session will be available on that playlist a little later today. Also linked was a short survey to help us improve our TVE sessions. So before you all leave, I want to share the TVE sessions that we will have next. At 1 p.m. today in this room, we will have a presentation on origami, and we will be back with Happy Math Hour next week at 11 a.m., where Math 1314 will cover properties of logarithms, exponential, and logarithmic equations, and Math 1324 will cover basic matrix operations and inverses. Our 1 p.m. session next week will be a presentation, When I Grow Up, I Want to Be a Writer, by EPCC alumni and author Isela Graels. Thank you all for coming in today. We hope you all have a lovely weekend. If you have any questions, feel free to use the chat box or your mic. We hope to see everyone again for Happy Math Hour.